All right, the problem is container with most water. Essentially, you're given an array of numbers that represent the heights of bars that are all distance 1 apart from each other, and you want to find the two elements that will allow you to have the largest area. So for example, this one here is 8, this one here is 7. So they're 1, 2, 3, 4, 5, 6, 7 apart, and the minimum height here is 7. So if you made a container out of this whole spot, you could have an area of 49. Now you couldn't do an 8 because if you filled the water up here, it would spill over this side. So it comes down to the minimum value that you're using. So you want to just find the max area you can make with all of these heights. So here's a, yeah. So the way to do this, let me just copy this real quick. So the way to do this is to look at first, pretty much just do the I guess the widest set that you can do. So this whole set, and see what you can make with this. So the way to see what the area is given to I guess heights, you take the minimum height. So this one's 1, this one's 8. You take the minimum one, this one. So min of both heights. So let's just call it h1, h2 times the distance, which would be, I believe, just the right index. So right index minus left index. So for example, if this is 0, 1, 2, 3, 4, 5, 6, 7, 8, you'd say 8 minus 0 is 8 times the minimum height, which is 1. So this area is 8, which makes sense because you're going 1, 2, you're going at a height of 1 all the way across. So 1, 2, 3, 4, 5, 6, 7, 8, right? So then we'll keep track of that, right? We'll set our best area. That's what we want to keep track of. We'll start that at like -1 or negative infinity or whatever, just so the first one will always be better than it. So we say -1, we come down here, we say 8. Is that better than best? Yes, it is. Let's save it. Let's go to the next one. Now, the question is, how do you know which next element to go to, right? We obviously need to either move this pointer or move this pointer. Obviously, if this one's less, we probably want to move that one, right? Because if we move this one, we have a possibility of this item, going down, right? And we want to maximize the heights. So to maximize the heights, we just need to say, if we have to get rid of one, let's get rid of the smaller one. So we'll move this pointer over and repeat the process. So we'd say the minimum height, which is 8 and 7, we'd say 7 times the distance. 8 minus 1 is 7, 49. This happens to be our best, the answer for this problem, but we'll just keep going to show the process. So now we'll move the pointer of the smallest height, which is this one. Same process. The minimum guy is, what is that, 3 times 6 equals 18. Is that better than our best? No. Okay, decrement, remove the smaller guy. Now, this is an interesting case. All right, let's do the thing first. Which one's the minimum item? Well, they're the same, so okay. Times right minus left, which is 6 minus 1, which is 5, equals 40. Okay, still not better than best, that's okay. But the question is, when they're the same heights, which way do we decrement? Or I guess, which pointer do we move? Do we move this guy over here? Or do we move this guy over here? And the answer is you can do either. Which, for me, that took a while to grasp, because the way I think of it is, looking at the next bar right now, wouldn't you think that there's a preference, right? Wouldn't you think you'd prefer, if you have to move one of these, wouldn't you prefer to move this one so we get a larger next height? Because if you're able to move either, then you're thinking you could either go here and your next height would be a 6 times a 4, so 24. So if we move left, it would be 24, right? But if we went back, and we move this one instead, now we have a height of 4 times 4, which is 20. So you're thinking, how would we be able to do both if this one very clearly gives us a smaller number? Well, the trick to this is that essentially in this case, either of those moves, although one looks better than the other, they're still both less than our best, right? And the way to look at this is, let's say the next item, let's just assume we're going to move right. If the next item is very tall, right? Like let's say it's even tall enough to, I guess, compensate for the decrease of area by lowering the width. Let's say it's even that tall. It doesn't matter, right? Because if this item is over here is 8 and this one's 8 and we're moving this guy to a taller one, let's just say this is like 12. This is still going to be bottlenecked by 8. So it doesn't actually matter that this item here is taller than this, because it's still bottlenecked by the other bar, which we already know is the same height of the one we just moved from, right? Now, if the item's lower, so the point with that being, I should also mention, because it's bottlenecked, we know that this area will necessarily be smaller than our previous one. This will be smaller than our, than our 40 or whatever it was. Why? Because, again, because we know it's the same height, so we know we're not gaining anything on the height, right? And then because we know we're moving into a smaller width, that automatically lowers our area, right? If our height stays the same, if our minimum height stays the same, and this lowers to 4, obviously 8 times 4 is always going to be lower than 8 times 5. 8 times 3 is always going to be lower than 8 times 4, that sort of thing. So if it's taller than our previous guy, it doesn't matter. We're still bottlenecked by the other one. Now, if it's smaller, right? If it's smaller, like this one is, then what it comes down to is we know for a fact that we'll still have an overall area that's smaller, right? Because we're losing width, so this number goes down. We're losing height because it's less than this, so this number goes down. The area is automatically smaller. It's not going to beat our best. The only situation in which, moving inwards will make our area bigger is if we have a really, really large numbers, right? But for that to happen, we need 2 really large numbers, right? So let's say these guys are really large. Let's say these guys are like 12 each. In order to get to this area that's larger, I don't know if that checks out. 12 times 2 would be 20. Okay, let's say this is like 50, and let's just make it really easy. Very clearly that even though this is a small width here, the height is enough to compensate for that small width and still be a greater area than our best. That's the example I'm going for. If this is the case, we would need to move both of these anyways, right? So, let's just say we moved at the point where we had both of these, we just chose the left one, or the right one to move left. So now our pointer's here, and our pointer's here. We'd say, okay, this is whatever, this is small, doesn't beat our best area. Because this guy's small, let's go here, right? Once we get here, let me change the color. Once we get here, this is now greater than this guy. So now we'll increment this guy. So now we're here and here, right? And now we're at the point where this is now greater than that. So the point being, when you're at the same height, it doesn't matter which one you go to, because if it's greater than it, it doesn't matter. It's still bottlenecked by the same height, based on the fact that you know the other one is the same height. If it's less than it, it doesn't matter, because you're automatically going to lose area because you're losing both width and height. You're automatically going to have a smaller area, which will mean it's obviously not better than your best, right? Because let's say this guy was the best, losing area at all, losing height, losing width, losing both is going to be smaller, so it doesn't matter. And if there is an answer within this solution, then we'll get to that eventually, right? Because if there's an answer within the solution, that means the bar there is going to be much greater than this, right? Greater than it, enough for the extra height to compensate for the width, the smaller width. So we'll get to it eventually. That's why it doesn't matter which way you go when the bars are the same. So that's the solution pretty much. So we start with the best. We'll just call it -1 because the area in this case can't be negative. So this is a way to say, okay, whatever our first area is, no matter how bad it is, it's going to be better. Just to, save it. Set our left to 0. We'll set our right to the length of height. I don't know why they call it height instead of heights, but whatever. And we'll say while left is less than right. We'll say the area, remember it's the minimum of the left height and the right height. times the distance, times right minus left. We'll say best equals the max between the current best and the area, whichever one's bigger. Return best. I think that's it. I don't know. I need to increment and decrement left and right accordingly. Of course, there's going to be an infinite loop. So if height left, and we'll just, in our case, we'll just assume if we have the equals, we're going to move left. It really doesn't matter. It could be right, like I said. If the left height is less than or equal to the right height, then increment left, otherwise decrement right. This is I believe, an O of n solution. Constant space, linear time, because you're doing a two-pointer technique, you'll never go through any element twice, right? So yeah, there we go.